we're going to begin with something that is the source of everything we're going to talk about in the entire class, and that is charge. I like to give simple, plain-spoken definitions of things. So charge, we'll say, is a property of matter that creates force. A property of matter that creates force. Even the initial concept of charge can get confusing because we have to jump between charge at the microscopic scale, the scale of atoms and molecules, to charge at the macroscopic scale, the charge of you and me in chalk. Okay? So since that gets confusing, I like to start by describing it in both worlds. Okay? So we're going to start with microcharge. So to see where a charge is at the microscopic scale, you have to draw something that you've probably seen before. N, P, and then like that, with an E out here, and an E out here, and an E out here. So you've probably seen this before. If you're from the 50s, you might be cowering under your desk. This is an atom. Okay? This actually is a specific atom. This is lithium. Because you keep up with elements based on their atomic number, based on how many protons in the nucleus. So 3 protons, it must be lithium. Lithium, very cool element. It was used, it makes grease, and it makes you feel better, and it makes nuclear weapons, and Nirvana wrote a song about it. So there's the 4 things I know about lithium. That's all I got. So now let's look inside this lithium atom and see where the charge resides. Well, it's in these subatomic particles. So we can look at the proton and ask ourselves, what is its charge? Charge of a proton is plus 1e, where E is the unit. E means elementary charge unit. It's defined as the charge of a proton. So this is 1.00, as many zeros as you want. The charge of a proton is exactly 1e. There's also, in the nucleus, there's the neutrons. And the charge of a neutron is 0. The neutrons are neutral. 0e. And then flying around the outside are the electrons. And electrons are negative. So its charge is minus 1e. Same amount of charge as a proton, just the opposite sign. One thing to stress is that E does not mean electron. Sometimes people see that E and they think, oh, that must be a negative charge. The unit must be negative. It must mean electron. It doesn't mean electron. Often we draw little e's to mean electrons. Sometimes we write an E and we mean this particle an electron. Sometimes we put a negative sign on it to clarify that it's an electron. But when you see it next to a number, you have to use your context and realize that doesn't mean electron. That means elementary charge unit. And it is not negative. It is also not positive. It's just a unit. Units don't have signs. The sign comes from the number in front of it. Okay? So if you see a number in front of an E, if it's a plus, then you know it's positive. If you see nothing, we assume nothing means a positive number, so that's also plus 1e. But if it's negative, we'll put a negative in front of it. Okay? But E is not negative. E is elementary charge unit. We can think about the difference between the microscopic and the macroscopic scales by also giving you the charges in terms of the macroscopic unit of charge, which is the coulomb. So the charge of a proton in coulombs is 1.6 times 10 to the minus 19 C for coulomb. The charge of the neutron is 0 C. Regardless of the unit, it is 0. And the charge of the electron is the same, it's just negative, minus 1.6 times 10 to the minus 19 coulombs. So a big jump between the microscopic and the macroscopic worlds. We can also, while we're thinking about it, look at the mass. We can also see the jump, or the difference, in the mass. Mass also has a microscopic unit, U. So the proton's mass is 1.007 U, where U is the unified atomic mass unit. The neutron has a very similar mass, sitting here in the nucleus with the proton, 1.009 U. And the electron, we think of the atom is having a heavy nucleus with light electrons sort of flying around in orbits, and sure enough, the electron's mass is very small, 0.0005 U. If we want, we can think about the macroscopic scale, and we can write these numbers in terms of kilograms. And let's do it. So the proton mass is then 1.67 times 10 to the minus 27 kilograms. So an even bigger difference than in the charge, 27 orders of magnitude in the mass. The neutron, I'm going to write with the same number, 1.67 times 10 to the minus 27 kilograms. And I'm writing the same number because here I kept up with it to 4 places, and here only 3. So pretty much if you're keeping up to things with sort of 1%, and our homework is only within plus or minus 5%, then these are essentially the same. Right? This is a very small difference. And if you are really keeping up with things only to about this level, the electron mass comes out very small, 0.0009 times 10 to the minus 27 kilograms. So again, if you're just keeping up with it to sort of this level, you can pretend the electrons weigh nothing. Right? If you're just estimating based on the mass of something how many electrons and protons and neutrons it has, you can pretty much ignore the electrons. They don't weigh very much. And they're similar in number to the other particles. Okay? So now let's think about how these things get charged up.